Now that we've taken a look at the theory behind solving these higher ordered linear differential equations with constant coefficients, we're going to actually look at the question, how do we solve them? And specifically in this video, we're going to ask, how do we solve linear homogeneous differential equations with constant coefficients? And as we're solving these equations, we want to make sure we understand the exact form we're dealing with. We're going to see a constant times maybe a second derivative plus a constant times a first derivative plus a constant times y. But what's important is they must equal 0. That's what makes them homogeneous. Homogeneous equations always equal 0. Now, when we have this linear homogeneous differential equation with constant coefficients, we're going to transform it to what's called the auxiliary equation, where we're going to replace each derivative with the variable. We can pick any variable. For this video, we'll use the variable m, raised to the exponent of whatever derivative it is. So this would become am squared plus bm plus c equals 0, because the second derivative becomes m squared and the first derivative becomes m. When we have this auxiliary equation, we have one of 3 possibilities for the solution. There could be 2 solutions. We'll call them m1 and m2. And when that happens, it turns out the solution is of the form y equals our first constant times e to the first root times x plus the second constant times e to the second root times x. If it turns out that there's only one root, because that's a perfect square, you could say it's a repeated root. The form is very similar. It'll be y equals c1 e to the mx plus, for our second solution, if we just did e to the mx, it would not be linearly independent. So to make it linearly independent, we're going to multiply by x, and it'll be c2x e to the mx for the second root. The other solution that could come up is it could have complex solutions. Maybe complex solutions alpha plus or minus beta times I. If we end up with complex solutions, we say the solution is y equals e to the alpha times x times the first constant times the cosine of beta x plus a second constant times the sine of beta x. And your textbook provides a decent explanation of the derivations and why these solutions work on the 3 different solutions. But what's important we know how to do is use these 3 important formulas, depending on if there's 2 solutions, 1 solution, or 2 complex solutions, in order to express our complementary solution. So let's do some examples to see if we can use these formulas. First example we're going to take a look at is 2y prime prime minus 5y prime plus 3y equals 0. Changing that to the auxiliary equation, we have 2m squared minus 5m plus 3 equals 0. This equation does factor nicely for us. It's going to be 2m times m and 3 times 1 if they're both negative, which means we have solutions m equals 3/2 and positive 1. Because we have 2 unique solutions to the auxiliary equation, we know the solution to the differential equation is y equals our first constant times e to the 3/2 x plus our second constant times e to the 1x. And that becomes our general solution to the differential equation that's homogeneous. Let's try another example. Let's try 4y prime prime plus 12y prime plus 9y equals 0. Again, we'll look at the auxiliary equation where the primes get changed to exponents. 4m squared plus 12m plus 9 equals 0. This one also factors nicely. 4m squared is 2m times 2m. 9 is 3 times 3, and they're both positives. What we really have is 2m plus 3 squared equals 0, and only one solution of m equals negative 3/2. Because we only have one solution, we've got the second case, where now we can say this is y equals c1 e to the negative 3/2 x plus c2, and we're going to have an extra x multiplied in there to make them linearly independent, e to the negative 3/2 x. And this becomes our solution to the homogeneous linear differential equation with constant coefficients. Let's take a look at a third example. Let's do the example y double prime minus 6y prime plus 13y equals 0. This leads to the auxiliary equation m squared minus 6m plus 13 equals 0. This one does not factor nicely, so I'm going to complete the square on it. You could also use the quadratic formula if you wanted to, but completing the square is not bad because the middle term is even. I'm going to subtract 13 from both sides, and then to figure out how to complete the square, I take that middle term of negative 6, divide by 2, and square it. That's going to be 9. So I'm going to add 9 to both sides so that it factors to m minus 3 squared equals a negative 4. And now if I take the square root of both sides and add 3 to both sides, I end up with my solution that m is equal to 3 plus or minus the square root of 4, which is 2i. It's the square root of negative 4, which is 2i. Because we have a complex solution, we use our third case and write that y is equal to e to the real part, 3x, times c1 cosine of the complex part, 2x, plus c2 sine of the complex part, 2x. And this becomes our solution to the differential equation. Now, all three of these examples, we have looked at second-order differential equations, but this same theory can extend to higher-ordered differential equations. Let's try one last example. Let's do the third derivative of y plus the second derivative of y plus 8 times y's first derivative minus 10y equals 0. Using the exact same logic, we'll build an auxiliary equation where every derivative is an exponent. So instead of third derivative of y, we have m cubed plus m squared plus 8m minus 10 equals 0. This one might take a little bit more work to factor, as there's no common factor I can pull out. I might try and see if I can use synthetic division to pull 1 out, using coefficients of 1, 1, 8, and negative 10. Bring down the 1 times 1, add them to get 2 times 1, add them to get 10 times 1, add them to get 0. And that did come out. So x minus 1 is a factor. And then the other factor is 1x squared plus 2x plus 10 equals 0. Setting each factor equals to 0, that second factor doesn't factor at all any further. So I do know that x equals 1 is a solution. But on that other one, x squared plus 2x plus 10 equals 0, I'm going to complete the square on that one as well. So I'm going to subtract 10, take half of 2 and square it, and add that to both sides. So that's x plus 1 squared equals -9. So then taking the square root of both sides and subtracting 1, running through the basic algebra a little quickly here to get -1 plus or minus 3i. So we've got a single solution of x equals 1. We've got a couple complex solutions. We can put that together using the same logic that y is equal to, the first solution is real, so it's c1 e to the 1x, plus the second set of solutions are complex. So we'll use our complex rules. E to the -x times c2, now we're on our second constant, cosine of 3x, plus c3 sine of 3x. And this then is our solution to the third-ordered linear differential equation that was homogeneous with constant coefficients. These are not very difficult, but you do want to get comfortable with solving them. So take a look at the homework and practice these. And in our next video, we'll look at what happens when they're non-homogeneous and it equals to a function rather than 0.